right, so today we are here to talk about tutorial week 4 we're calling it AI for healthcare practitioners, but it's the Clinicians program that is being run through Michener and Vector Institute. And Flora is going to take us through the tutorial. So Flora, first, who are you? How did you come to be in this program?
Well, I have a background in computer science and human factors engineering, but my main passion really is healthcare, especially healthcare as it relates to helping kids with disabilities. So after I finished my master's, I decided to apply to a hospital position, and so I landed a position at Holland Blairview Kids Rehabilitation Hospital, and as an assistive technology consultant. So it's actually interesting because I was part of a clinical team that work with kids with communication difficulties, kind of like alternative ways of communicating using technology and other methods. And I really loved it because it, gave me a chance to work with families, work in healthcare. And then about 3 or 4 years ago, I decided to move into research because I thought, that's a really interesting area to grow and discover new knowledge. And so then I've been working in research for the past 3.5, 4 years. And within that time, I started getting really interested in data science and AI partly because of my technical background, and partly because, I'm hearing so much about this. Like, what is this AI stuff? What is this data science stuff? And so I started taking courses at U of T, getting involved in all these different organizations related to AI and healthcare. And this kind of brought me to connecting with Shingai and to be a TA in this course. So I'm really excited to spend, these weeks with all of you and to kind of learn and explore together.
Fantastic. And we are very, very fortunate to have you. I should probably introduce myself once again. My name is Shingai Manjengwa, and I'm the course director in this program. I'm also director of professional development at the Vector Institute. So my job at Vector is to take all the cool AI research that's being developed, and then I package it into content that industry can absorb. In this context, you are industry. So we are packaging artificial intelligence models, concepts, tools, and techniques into materials that you can appreciate, that you can start to use, that you can critically evaluate, which brings us to this assignment. So a big part of Flora's work in general is accessibility and inclusivity. So Flora, it makes sense that you've done our natural language processing assignment. Do you want to just start with what is natural language processing? And just start there.
Yeah, natural language processing is actually a really big field nowadays in AI. And it's really, it really comes down to the idea that so much of the information that we have is in text. So if you think about it, your electronic medical records that you use in your medical institution every day, so much of it is in text. In fact, I've heard someone say that it's 80% of the information that we have is in text. And the problem with that is a lot of this textual information is not easily accessible or easily processed by a computer. So when we talk about natural language processing in the context of machine learning and AI, we're really talking about, how do we take all this text and convert it into information or data that a machine can understand in order to extract the patterns from this data. So this is sort of the kind of the gist of the, the topic and the assignment, and we'll go into it a little bit more with a practical example of what we mean by that.
All right, well, let's get into it. So I'm going to ask Flora to pull up the natural language processing model that she has created for this tutorial. This is a legit model. It works. You could use this in theory, but we did this just so you'd really get a sense of when data scientists or machine learning researchers are sitting at their desks and say they're working on a model, what are they doing? This is what they're doing. So Flora, I'm going to ask you to just walk through, take us through what you've done, why you've done it, any context, talk us through the results, and then talk us through any of the visualizations that you have in your model. Over to you, Flora.
Hey, thanks so much, Shingai. So the idea of this particular assignment or project is that we have a data set consisting of a whole bunch of medical notes, and we'll see some examples of what those notes look like. So they're all in text. So what we're trying to do is to see if we can take that kind of raw and structured data and create a model to predict a patient's diagnosis just from that text. So that's the general context. So here you see, this is the collab notebook where I have written my code. One tip, I guess that would help everyone is if you go up to view and table of contents, this actually shows you the whole kind of outline of everything that I'm doing within the script. So it's a good way to kind of keep track of what's going on. So you see that we're importing the data set, selecting the features, exploring the data set, pre-processing the data and so on. And I'll go through each step, but it's helpful to kind of follow along just to see the outline of what's happening. So I guess we'll jump into the code. I won't go into too much of the technical details, but I'll highlight, a few things that would be interesting for you to understand as you're sort of evaluating this model. And the goal of this is not to understand all the technical details, but to say that if, a data scientist like me comes to you and says, what, I've built this really cool use case. I think I can just take medical notes and predict the patient diagnosis. It's going to work great. What would you say as a clinician? Like, is this something that is useful? Is this something that is feasible and actually clinically relevant? So that's something to keep in mind as we're going through all of this code. So I'll just start walking you through what's in the code. So the first thing here is just a note to change one of the settings in Google Colab, and you see the instructions here. And we're talking about GPU. And I think in the previous week's assignments, you probably would have already, talked a little bit about GPU when we talked about vision processing. But it's the same idea where because we're using a neural network to run it, it's much faster in the GPU. So it's just a simple setting that you have to change in Colab, and just a reminder to do that before you start running the code. So within the code itself, first we import the data set. So the data set is a publicly available data set consisting of medical records over 10 years that has, medical notes in addition to the medication that was used and the diagnoses and so on. But for the purpose of this assignment, we're just going to focus on two things, which is the one is the medical note itself in text. And the second thing is the diagnosis, because this is what we're trying to get the model to learn how to predict. So you would first run this part of the code to download the zip file that contains these data sets. And there's nothing else you need to do, really. You run it and it does its thing, and then out comes the zip file. And what we want to do is load these two particular files. And the reason why they're two separate files is because one contains the records representing the patient's encounter with the healthcare system. So it's got all of these, like I said, clinical assessments, medical reports. And then the other one is actually a separate table containing the actual diagnoses. And I think this is probably the case because it was extracted from a relational database table that has different tables representing, different aspects. So what we want to do is we want to download these two files containing these two tables of information, and then we'll merge them. So when you first download it, you'll see that there are different ways of, looking into the data. A really simple way in Python is to just do .head on the data frame. And you see that these are the columns, and each row represents the patient's encounter. And it's got lots of information. We're not going to use the majority of this information, except for when we see here at the end, we see a column called SOAP note. And so this is the actual column containing the text medical data that we're looking at. The other table here is the DF encounter DX diagnosis. So again, it's got lots of columns, but we're mainly interested in this description column, which is the actual diagnosis, or the description of the diagnosis that we're trying to predict. And to merge these two tables together, to connect them together, we use the encounter ID, which connects those two tables together with the records. And the way we do this is a really simple one-line, Python code that merges these two tables using the encounter ID as the key. And now, if you look at this, it would have all the information from one of the tables. And at the end, you can see that it also has the description as well. So now all our information is in one table. But as we mentioned, we really only care about the SOAP notes and description for this purpose of this assignment. So even though we have a lot of these columns, as you can see here, you can dot columns. What we want to do is we want to select the relevant rows and columns that we're interested in. And so this is the way we can do it in Python, where we select the SOAP notes column and the description. And now we have a very clean merged view of the data sets, where one of the columns is the text and the other column is the diagnosis we're trying to predict. So this is great. And then as you're looking, to do these types of analysis, especially for healthcare data, anything that comes from an electronic health medical record system, you see that there's sometimes a bit of consistency. So for example, here you see for record number 8 here, it's NaN means it's null or empty. So there's no data here for whatever reason, it just wasn't recorded. So in that case, we want to clean up this database so that when you're running the model, all of the examples would have at least a text and a description, because you don't want anything empty going into the model for training. And so then we kind of take a look at how many records are empty, and let's just filter those out just to clean it up. And we call this part of it data cleaning, which is very often something that data scientists and people working in data science do spend a lot of time on, as you can imagine. So now we have this full data set called DF merged, and it's got all the complete set of information. It's got the text, medical text here, and the description. And so now we're good to go to start exploring it. All right, so now we go down to here where we start exploring the data set. So your first question would probably be, well, what does one of these notes even look like, right? So here's an example of how we would print, for example, the first item in these notes. And as you remember, in Python, everything starts with 0 instead of 1. So 0 would be the first record. And so you can see an example here of one of these types of medical notes. So this note is about a 33-year-old female that has mild spells of vertigo, mild headaches, and so on. And the diagnosis here is hypertension. So as you can see, this is a pretty good description of somebody that has hypertension. And here's another example. If you change this 0 to a different number, like 400, or anything, within the number of records that you have, you can easily look at another example. So this is an example of a male about 4 months old with an amputated shoulder coming in for a physical therapy visit. And the description is of the diagnosis is a disarticulation of the right shoulder status. So these are just a few ways of looking into the data set to kind of get a better understanding, because you really want to understand what's in the data before we even start to train the model. All right, so I guess going back here, another question that we would want you to consider is, okay, if you're looking at a note like this, how relevant is it to you from a clinical point of view? Is this a typical way that a note will be written? Is this the information that it will have? What do you think in terms of if you compare this particular note with something that you would see in your institution. Is that something that you would be able to kind of map to this format? So there's, so some things to keep in mind from wearing your clinical hats as we're going through this example. So an interesting thing that we noticed when we looked at these examples is that in the original notes, a lot of times the diagnosis, as you can see here, is actually part of the note, which, makes sense from the point of view of a doctor, writing down the medical history of the assessment. But in our model, what we want is to see if we can use the actual, the symptoms and the description of the text to predict the diagnosis. So if all of these medical notes already have the diagnosis in there, it's a little bit too easy for the model, right? It would just read like, oh, hypertension, then I know, of course, it's hypertension. So what we want to do is to make it a little bit more challenging for our model by removing the words related to the target or the label, or in this case, we're talking about the diagnosis from the actual medical text that we're looking at. So this is just some code to tokenize. And this is actually a very specific and frequently done, featured process in natural language processing, because yes.
Can I jump in with a question? So
yes.
Just making sure that we've really understood what this model is for.
Yeah.
Is that you're looking at those SOAP notes,
yes.
and you're gonna right now you do have a diagnosis in there, but you're gonna remove that diagnosis, and the balance, whatever text is left, we're gonna use that note to try and create predictions of a diagnosis.
Exactly.
Okay.
Yes.
Got it. And the reason that we take out the part of the note that has the diagnosis is that, as you say, it would just be too easy, right? The model would figure that out quite quickly. The structure of the neural network is such that it does look for the path of least resistance, so it would quickly pick that up. So you've taken out the diagnosis in the text, and the text that's remaining is presumably the kind of SOAP note that would be there before a diagnosis is made. Okay, yes, so this is excellent. So it's a predictive tool, and hypothetically, it could be used as a product or a tool that could assist clinicians to make diagnoses.
Yes, exactly.
Got it.
Yeah, very good point. Thank you.
So now we're moving into the actual, this is natural language processing, right? This is what we mean when we're running text models. So you were on the subject of tokenization, stemming, you were also changing everything to lowercase. Take us through this section.
Okay, so this is sort of a simple way to start processing this natural language, because when we think of natural language, we think of it in terms of paragraphs and sentences, but a computer, when it looks at features that it can use for a model, is thinking of it as individual tokens or individual aspects of the data. So if we break down a complete medical note, let's say, we can break it down into pretty much words and punctuations. So this is sort of what it's doing, is taking the text and it's breaking it down into words and punctuations. And all of these specific words and punctuations are called tokens. So each one of it is a sort of a separate unit that the machine can look at to decide, to find a pattern. So for example, words that generally describe hypertension, for example, they'll have similar tokens because they have similar words, compared to which will be different words than medical notes that are describing, let's say, a heart attack or something like that. So this is just an example of how we often do natural language processing, how we start processing the text. And again, as we mentioned, we want to remove the diagnoses, the word for the diagnoses from the text. And so this is just an example of how we would do it and what it would look like in the end. So what we're doing is we're taking the original text, we're separating it all into words and punctuations, and we're trying to match the actual output. So the output of this diagnosis is embolic stroke. So we don't want any words related to embolic or stroke in the input text. We want to take that out. So after we have transformed it into tokens, we match if there are any words related to embolic or stroke, then it will be removed in the transformed text. So this is just an example of how we would do this. And as Shingai, very nicely explained, this is just also an idea that, if we have a description of a medical assessment, can we use this model to predict the diagnosis? That's why we're training it this way. All right, so now we have the text. So that would be our input. So now let's look at a little bit more about our output, which is the description of the diagnosis. So as you can imagine, there are probably a lot of different diagnoses. And in this particular data set, it's probably a little bit simplified compared to what a normal, regular electronic medical record system would have. But these are all the unique types of medical diagnosis that is in this particular data set that we can see. So we see that there are many that are general medical exams and diabetes, all the way down to the ones that are less frequently used, like removal of sutures or critical distress or agony. So what we want to do is we want to think about it like, well, in order for a machine to find patterns, it needs to have enough examples of the same category. So if these ones here, we only have a few examples, it's probably, not good enough not enough examples for the machines to really get the patterns, to understand and come up with those rules. So what we want to do is to reduce the number of categories by combining some of these more rare categories together. So this is what we've done here. So we decided to say like, okay, so if there are any categories where there were less than 100 examples, so that would be the ones here, less than 100 examples. We want to combine it into a single category called other. And in this way, we see that this is the new count of the number of examples in each category, starting from embolic stroke. And now we have less categories and also more examples per category. But I do want to point out that it is going to be challenging for the machine to predict an other category because all of the examples here are very different from each other. And so it'll be, hard to, figure out a pattern because there really is no pattern. But the rest of it should be the rest of the diagnosis. We're hoping that there would be some kind of pattern in the description of it that can predict the diagnosis, but we'll see if that's the case when we start running the training.
And so, Flora, when we actually use this model in a clinical setting, hypothetically, the idea that there's an other is also a little bit worrying, because if you're a clinician and you enter the information, you enter your SOAP note and you say, all right, computer, give me a diagnosis, and the computer says other. That's also not fantastic for the end user there. Okay, got it.
Yeah, in a real setting to deploy this model, you would probably want to find more examples. I mean, this is a very small data set just for the example of this assignment. But in a real institution, the best way to go about this would be to actually collect more data and have more, good high quality examples so that the machine can properly diagnose, these different types of diseases. Yeah.
Awesome. Okay.
All right. And here you see a plot that's really the same, the visualization of these numbers here. And you can see in general how many examples are in each of these diagnosis categories. And sometimes we'll just refer to this as, the label or the target. But what we're talking about is the output or the outcome of the medical diagnosis note. So this is I think the 11 categories we now have to predict. So what we want the model to do now is to take the examples in the medical text that we have sort of pre-processed, and then see if it can predict whether or not the medical note is one of these 11 categories that we filtered down to. All right, so now we have the input, which are the medical notes, and the output, which are the diagnosis. So we can start doing sort of some standard machine learning type of processes. So I think by this week, you probably would have already gone through a few examples of what we mean by splitting into training and test data. So training data is really the data that the machine is looking at to figure out the patterns in the data. So that should be, a bigger chunk of the data that you're using. And a test set is a separate subset of the data that we're putting aside so that once we've trained our model, we can have some data that the model didn't use for the training in order to kind of really evaluate the performance as if it was, new data that comes in. How well does the model perform? Is it still able to predict just as well as it did on the training set as on this data that is never seen before?
All right, so wait. Flora, this is an important point. So let's talk through this point specifically. Sure. So our data set right now, after we've cleaned it and processed it, we've got a data set that has SOAP notes, and then separately, it's got a diagnosis. And the diagnosis we have is correct. Okay. Yes. So what we're going to do is we're going to randomly separate this data set, and you've said 75% and 25%. So 75% of this data, we are going to train the model on the SOAP notes, and it's going to learn what diagnosis was produced.
Yes.
Okay. And then it's going to run it on the testing portion of the data set. And it's just going to pull in the SOAP notes and then run the model on the SOAP notes, the one that we've trained on that 75%. And then based on that, we're going to see if it's able to accurately predict the diagnosis that is produced.
Yes, absolutely.
Excellent. And then you'll score the extent to which that it's able to do that, so we can assess whether the model is actually a good one or not.
Yes.
Got it. All right, off you go.
Awesome. Thank you. That was a great, excellent explanation of the train and test process. Okay, so what we want to do, as Shingai mentioned, is we want to set aside some of the training data and test data. And to do that, we can do it quite easily in Python by using this train test split method. And this is a very common method that you will see in a lot of different kind of these AI machine learning examples. And we are then seeing that we're just making sure that we have the correct number of examples that we expect in each of them. So we have about 2,000 in the training set and about 700 in the test set. So again, that's 75% here and 25% here. And as Shingai mentioned, from now, at this point, we're not going to touch anything in the data in the test set at all, because this is the data that we want to use at the end to evaluate the model. So at this point, we're going to use these 2,000 examples in the training set to see if we can train a model that can recognize the patterns in the text to predict the diagnosis. All right, so one thing that you might think of is well, what if there are some of these, smaller categories, and I've, randomly the machine has split them into the training and test set. And what if all of these examples had gone into the training set and, nothing in the test set? So I decided to put a plot here to kind of look at the the proportion or the percentage of examples within each category. So the blue is the training set, and then the orange is the test set. And as you can see, the proportion of data relative to the category is in both of the training and test sets is similar. So you can see that there are some examples of all of these categories in both of the data sets. And so this is just another way of making sure that the way we've split the data is is proportional, and it's a good way to represent what we're trying to test here.
So Flora, looking at this table, is this a table of a model that's been run yet? So if we look at that other category, are you telling me that there's quite a disparity between the trained data and the testing data, or have you not run the model yet?
Yeah, so that's a very good question. So this graph is actually not showing you the performance of the model that's been trained because we actually haven't trained the data yet. So what I'm trying to show in this graph is actually just the distribution of the data within each of these categories. So for example, the blue you see here is the training examples and the orange is the test examples. And we just want to make sure that within these two data sets, there are some examples of each of these categories within these data sets. So it's not anything related to the actual performance. For example, for other, what it's saying is that it's not that the testing results are better than the training. It's really to say that, oh, in the test data set, proportional to the rest of the categories, there are about, like maybe 0.16 or 0.165 of the data is in the other category. And in the test, there's about like, 0.13 of the test data is part of the other category. So it's just a way of looking at the distribution of the data.
Got it. All right.
Okay, awesome. All right, so as we will keep going. So another thing that we need to do, just because of the way the model trains and the model, expects certain values to be inputted, it expects them to be, it expects the categories to be represented as numbers. So here you can see that instead of hypertension, the model expecting the target to be something like 2. And we have 11 categories here. So an easy way to encode these into numbers is just to use this simple Python package called label encoder, and it will just take a set of text input and then assign a number to each of them. So in this case, it will be assigned from 0 to 10 because Python starts with 0, but there are 11 categories. And here you see a simple example. So after we've used the label encoder, we see that it's converted hypertension, pulmonary disease, and general medication to number 6 and number 2 and number 4. And then we can convert it back. So later on, when we're actually looking at the results and we want to see which of the diagnosis it's actually talking about, we can convert these output back into the text format that we can understand. So this is just another typical type of pre-processing that you would do in machine learning. All right, so now we get into a little bit more of the specifics related to natural language processing. So we touched on this a little bit earlier with the idea of tokenization, which is basically if you take a whole paragraph of text, you want to break it down into individual words and punctuations and even maybe parts of words. So this is what we mean by tokenization, to convert this whole paragraph of text into little tokens that the machine can use as features that it can learn the patterns from. And so now we also start talking about transformers, which I'll go over a little bit more when I go through the slides. But the idea of a transformer, it's sort of a machine learning algorithm that is really good for processing sequential data, and in particular, very good at processing text data. And over the years, there's been many different algorithms, to process sequential data. But the reason why nowadays, when you hear about transformers, is such a state-of-the-art method is because it has a really good, it's really good at being able to understand like the context in the sentence. So instead of looking at individual words or a few words at a time, it can actually process the entire sentence and sort of figure out the context of the sentence and the language structure itself. So that's the reason why transformers has really taken off, and it's really helped the natural language processing area grow by a lot in the past few years. So that's why we're using the transformers to train our model, because we want you to be able to get a sense of like, okay, this is sort of the state of the art of how we're processing natural language now. So one of the things that the transformers package can do is that it can help tokenize this type of text data. So here we install the transformers package, which is just a simple one line to download everything related to the package. And there are many publicly available pre-trained models. So what this means is that if you think about language, if you're a little kid trying to learn language, it's really difficult because you have to learn one word at a time and learn the context and learn grammar. And so if you're in the same situation as a machine learning engineer, it will take a lot of time and, more importantly, a lot of data before you can actually make sense out of this. So what a lot of the really big companies like Google, what they've done is that they've taken a lot of text from everywhere, from books, from Wikipedia, that has a lot of already standardized, good quality text data. And what they did was that they pre-trained these models so that when you use these models, it already actually understands language context. It understands grammar. It understands the parts of speech of words. And so, of course, it might not understand particularly what a clinical diagnosis would mean, but at least it understands the structure of language. So that's what we're using as sort of the base that we can train on to kind of speed things up a little bit. And it's I'll talk about this a little bit later as well. It's the concept of transfer learning. So you're transferring what somebody else has already done, all the learnings and all the understanding that is in those models, and you're just building on top of it to fine tune it to your particular situation. So in this case, I just wanted to give you a few examples of these kind of pre-trained and available transformer type of models that you can use in order to tokenize your data. And these are a few different examples. They call it BERT, which stands for bidirectional encoder representations from transformers. So this is what BERT stands for. And a lot of times you actually see it associated with the Sesame Street BERT. And it's just sort of there's no reason why it's associated. It's just, data scientists, having some humor. But BERT are really Shingai, did you want to jump in?
Yeah, I've got a question. So if we're using a pre-trained model, presumably we are quite dependent on the data set that was used for that pre-trained model. So already there could be bias in the pre-training. So we can start discussing bias in our model, but then just because we're using a pre-trained data set, depending on where we got it from and how reliable the data used to train that was, there could already be bias in the pre-trained data set.
Yes, that's definitely a possibility and something that we have to watch out for, especially because language in the end is produced by humans, and humans inherently have bias. So if something was trained using language from people's opinions, let's say, then that's already biased. Yeah.
So like social media, Twitter data
exactly.
would look, if that was used for the pre-training, that would be quite different to you mentioned Wikipedia and potentially some other data sources.
Yes, absolutely. Yeah. So you have to be careful which where your data is coming from and where your pre-trained model is coming from and what data it trained on, to kind of be aware of these types of biases. Very good point.
Got it. All right. So we're still encoding, and then we're going to train. All right.
Yeah. Okay. So we're almost there. The last part is encoding. So I just wanted to show you sort of what these tokens might look like. So normally, as we mentioned, you would think of tokens as words and punctuations, but the way that BERT and transformers do it is actually they do tokenize based on punctuations and words, but also parts of words. Because if you can imagine, a word can have many forms. It can be plural. If it's a verb, it could be, past tense, present tense. And so what we want is to take the root of the word and have the machine be able to kind of find the patterns between the root words, regardless of the grammar or the, plurality and so on. So this is something that's the tokenization methods in these transformers or BERT already does for you. So here's just an example of, 3 different pre-trained models based on BERT and the way they would tokenize something like standard medical text. And as you can see, there are, words that you can pick out like chest, and extremities and performed, heart, normal, and so on, but also parts of words. And so this is the way that the tokenization works in BERT. And it's actually a really good way to kind of let the machine, combine certain, tokens together to make a word instead of treating each word as a separate unit. So that is just an example. As you can see, overall, the tokenization is quite similar. So what we're going to do is use the standard BERT model as our base model for our training purposes. All right, so this is more encoding, and you don't have to understand all the technical details, but this is just really the idea of encoding is that we want to convert this whole block of text into something that the machine can understand. So we first break it down into, punctuations and words, and then the machine further does more processing to encode it into actual numerical values or numerical vectors that the machine can understand. But this is already sort of like all done for you as part of BERT, and it's just part of the pre-processing step. And we are now ready to train our model. So thanks for staying with us for so long. I know it's a lot of pre-processing, but that's a lot of what the data scientists go through to even prepare the data. So this is sort of the fun part of now we have all the pre-processed input data that's all encoded into a format that the machine can understand. So now we want to build our model. So here is how we would kind of define how to build a model. And again, this is more of the technical details. And I have a sort of a diagram in the slide to kind of make it a little bit more visual what it's trying to do. But the idea is that you're using this BERT layer as the base model, because what we mentioned was that it's already pre-trained to understand language context. And then we're adding this 2-layer neural network on top to basically fine-tune the results to what we want in our case, which is we want to predict the diagnosis. So we want the model to understand that, okay, this is the input of the text, and we want it to predict one of these 11 different diagnoses. All right, and then this is just sort of a little bit more of processing. We already talked about here, we're processing the input data by encoding it using BERT, and we're formatting the output labels to be numerical so that the machine can use it for the prediction here. All right, so now we built the model, and you see here in this output, that our inputs are these different layers, which are really just the encoded data from the text input. Here we have the, here we have it connected to our 2-layer neural network. And that's basically our model. So basically our data will flow from the input, it's going to get encoded and pre-processed. BERT's going to help it understand language structure, and it's going to be passed into this kind of a small neural network that can actually do the classification task. And that is how we are going to train our model. So once we have defined it, then we can run it. So by this point, you probably have had some awareness of neural networks, especially having gone through the previous assignment with vision processing. So the idea is that the idea of neural networks is that you would give the machine a lot of different sets of training data, and it would try to make a prediction. So of course, the first time it makes a prediction, it's probably going to be wrong because it randomly initialized, all of the weights and all of the parameters. So what it does is that it goes back and figure out, well, which part of my model is making the biggest mistake. So let me tweak it a little bit to make it better. And so then it does that and it tries again. And it's like, well, it's still not quite right. Let me tweak it a little bit more. And it tries again. So each of these iterations, each of these, trials is called an epoch or an iteration. And here, this is exactly what we're doing. We're defining 10 epochs. So we're telling the machine that okay, we want you to, try 10 times as best as you can to make this the most accurate model that you can make by tweaking those parameters. And at the end, we'll evaluate this model to see how well it does on a different training set, a different test set. So as you're training it, it will actually output what it's doing in each epoch. So here you see epoch 1 to 10. So what it's doing is that it is training based and then outputting the accuracy of the classification. But at the same time, is also using sort of a separate small data set that is set aside called the validation set, because we don't want it to be looking only at the training data, because it could be fitted too closely to the training data or maybe not close enough. But we want something that's less biased to the whatever we have in the training data. So we have a separate set called the validation set that we set aside to evaluate the performance as we go along in the different epochs. So here you see that at the beginning of training, of course, we start with no data at all to about 0.5 of the accuracy, so about 50% accurate. So I mean, that's not bad actually for the very first epoch. And then as you see that as we continue training, it gets progressively better. So in the second epoch, it's able to go from 0.5 to 0.7, 0.7 to 0.8. And then as you can see, it's increasing, but not by as much. And here it actually was, didn't really improve beyond this point, and then it just kind of inched up a little bit. So this kind of is a really great way of evaluating the process of the model training to see at what point should you stop, and at what point would the model be overtrained, and maybe you start getting performance that's not as good. And the reason why I chose 10 epochs for this example is because I actually tried different numbers, and I looked at the graph to plot the here you see on the bottom here, it's a plot to compare the training accuracy and the validation accuracy as we go through all these different epochs. So because of the way we've set up the neural network, the training the training data or the training part of the data, it's going up, but it's got a little bit of so it needs a little bit more training before it can get to the right accuracy. So whereas the validation data, you can see that it's kind of also coming up, and they're both kind of plateauing at this point. So that's why I picked 10 epochs, just because on the graph I can see that, they're both plateauing at this point, and it's probably not going to improve much after that. So I'm going to stop training at this point. So this is, yeah.
So Flora, just to clean up our understanding of that. So when you split the data into training and testing, you didn't actually put aside a specific data set for validation. So where does the validation data come from?
Good, very good question. Sorry about skipping that part. Okay, so here when we define the training, so model.fit is where we define how we want the model to fit the data. There's actually one of the parameters is called the validation split. And so this 0.2 means that we tell the model, as you're training it, we want you to put aside 20% of this data to be the validation data that validates the model during the training process. And so that's where this this separate split is from, and not to be confused with the test set, which we have already put aside and is not used at all during the training process. But this is just another sort of a 20% of the data that's split off to evaluate the model during the training process.
Excellent. And you also mentioned another great word, which we'll come across in multiple places, overfitting. So in regular language, when we say overfitting in this context, we don't want to train this model on this exact set of SOAP notes, because anytime we try and test it against other SOAP notes, it's not going to perform very well, right? So that's a very important word to bring in. So yeah, maybe just if you've got any other comments on overfitting, and you also said overtraining. So yeah, just a few more comments on the implications of those terms.
Yeah, so overfitting is when you have trained your model so well on the training data that at some point it just memorizes what it is, right? Like, let's say if it looks at a SOAP note so many times and figures out that, like, oh, every time I have to, the name John in there, it's going to be hypertension, which, it makes no sense. But when the model looks at the same data over and over again so many times, it's going to start memorizing some of these things. So that's not what you want the model to do, because when you have a new set of data, like, there's no reason why somebody named John would have hypertension. So you want the data to be at a point where it's generalizable and only really using the features that make sense in the greater context. And so that's what we mean by overfitting, when the training is so closely matched to the training data, but not, as generalizable to something, to new data that's coming in. Okay, so.
And you mentioned overtraining. So if we set this to 100 epochs, what do you think would happen there?
Yeah, at some point, the model the performance actually will not increase. And in fact, it may start to decrease because now, again, you are overtraining on the same data. And so that is not making any kind of incremental improvements on data that it hasn't seen before. So now it's just kind of training over and over again on the same set of data. It's starting to memorize it. And then when you start giving it new data, it's actually going to do worse, because then it's going to start using features that are just specific to your training data and not something that can be generalized to new data that comes in. Yeah, very good questions and very important concepts to understand for machine learning and AI.
Yeah, we haven't rehearsed this at all.
But lots of good points. Thank you. And Shingai, feel free to jump in to clarify any of the points. This is really great. All right, so we looked at a bit at the graph on how we can kind of monitor the training process. And so here we see the dots are the training accuracy and the validation accuracy. And you see at some point around 10 epochs, they sort of level out. And so this is where I've decided to stop the training. And so at this point, we'll call this our, our final model. So let's say, okay, this is, it seems like this is as good as it'll get on our data. So what we want to do next is to test it on data that it's never seen before. So if you remember, we put aside a test set, the 25% of the data at the very beginning of this whole model training process. So now we can make use of this test set because this is data that the model has never seen before. So how well can it use this data, use the SOAP notes in this data to predict the diagnosis if it's, never seen the same SOAP notes before. So when we get to this section, we are now evaluating the model. So as we mentioned, we're trying to, there are different evaluation metrics for a machine learning model, but we'll first kind of use the accuracy score, which is a pretty straightforward score to understand. So what we're doing is that we are having this test input. So test input is the SOAP notes from the test set that it's never seen before. And we're asking the model to predict what it thinks the classification, what it thinks the diagnosis is for each of these examples in the test set. And so it would make So what it actually does is that we have 11 categories. And so what it does is that for each category, it will kind of give a prediction or score between 0 to 1 on how likely that SOAP node is matched to that category. So if it thinks something, it's really, the words in this test input example is very similar to words I've seen before related to hypertension. So I think there's a 0.8 chance that the SOAP node may be talking about hypertension, and maybe only a 0.05% is talking about shoulder dislocation or something like that. So out of these 11 categories, it's going to give a score to each of these categories on how well it thinks that it will match that category or label, and then we are just taking the one that has the highest score and saying that that's going to be our prediction, which is not to say we're 100% sure that this is the diagnosis. This is really just the best guess of the model that we're picking. And then what we want to do is we want to compare what we're predicting, which is the Y prediction here, with what is actually the diagnosis, because you remember in the test set we actually know the diagnosis. We're just not letting the model see it when it does the prediction, but we can compare it to what we're predicting to see how often we get it right. So in this case, we can calculate the accuracy score overall based on the test set, and we get to 0.85, so 85% accurate, which is pretty good for just training for 10 epochs and having sort of a small data set. So this is another example of how powerful this new transformer technology is, and the way it understands language and able to capture the essence of text information. So there are other ways to look at the performance, but before we do that, one other question we always want to have is, well, how does this test data sets performance compared to our training data? Because as we're training the data, we also capture the accuracy information. So is our test set, on basically, is it doing much better or much worse or about the same, on data that it hasn't seen before compared to data that it was trained on? And so in order to do that, we are going to take the accuracy on the training set, which we've gotten as we were doing the training process, and we just graphed it. And as you can see, these are actually quite similar. So we can see that we can say is that, well, you know what, we think that the data is generalizable because the performance on this test set data that it's never seen before during the training process is actually quite comparable to the performance on the training data itself. So this is one way of kind of verifying that what the model that we built is actually usable for new data as well. And there are a lot of other ways to look at the performance of a model, but in particular, especially for classification models, the confusion matrix is a really good way of visualizing what's actually happening. So So I'm not sure if you would have encountered this kind of idea of a confusion matrix during this course already, but the basic idea is that you have this, table where one side of it is talking about the actual diagnosis, and the other side is the predicted diagnosis. It's an easy way of seeing, based on each of the categories, whether or not the predicted diagnosis is the same as the actual diagnosis. So if it's the same, then you see that it will match up. So for example, here, the general medical examination, there are 137 where the machine or the model predicted that it's a general medical exam, and in reality it actually was, so it got it correct. And all these other ones outside of this diagonal are examples where the model predicted something wrong. So here you can see, for example, the actual diagnosis is acute renal failure, but there are 7 of them that were predicted as a general medical examination. And one other one I wanted to mention, and Shingai also mentioned that as well, is that in the other category, there's kind of more of an error because, for example, a lot of the actual categories that are considered other were predicted as a general medical examination. But this was always going to be a category that's challenging for the model to predict because all of the examples in this category are very different from each other. But overall, we just wanted to show you what a confusion matrix looks like and how you can understand how to read it. And it's a really good way of getting particular information, for example, knowing that, let's see, what's a good example? Knowing that embolic stroke, for example, is often confused with hemorrhagic stroke and so on. And so now when you think about it in terms of a medical context, or if you're now evaluating the usefulness of this model, then you can kind of think about it as like, well, if it makes these types of errors, what is the risk in a machine giving a wrong prediction like this? Is this something that is still usable in a clinical context, or what needs to be improved before me as a clinician, I can trust it? So this is a really good way of kind of getting a good understanding of what's happening in these types of classification models. All right, so another way to evaluate the model's performance is using these scores that are often used for classification called precision recall and F1 score. So precision and recall, you've probably learned already during the course, are ways of looking at the, the results. So precision is how many of what the model predicted as positive are actually positive. So if you look at the formula for prediction, we are dividing the true positive number by the combination of the true positive and false positive. On the other hand, recall is talking about how many of the actual positives are truly predicted by the model. So this is sort of talking about how many we're missing that are actually supposed to be there. So the formula for recall is we divide the true positive by, in this case, the true positive and the false negatives to get that value. The F1 score is actually a weighted average of the precision and recall scores. And or sometimes we call it the harmonic average. And the reason why we want this type of average instead of just a regular average of the two scores is because in the example, if you think about, let's say a model has very good precision, but 0% recall. So in which case it's predicting, everything that is predicted is correct, but it's, missing so many of the patients that is not diagnosing properly. So we don't want this model, we want to show that this model is actually not great. It's not 50%, 50% well done. It's actually less than that because we want to kind of make sure that both precision and recall are at a reasonable value. So that's why we have the F1 score, which is sort of a way to weight the average of both the precision and recall as one score, but in terms of making sure that neither one of them are too extreme between 0 and 100. So now when we print out the classification report, we'll see that each of these diagnoses has its own particular precision, recall, and F1 score. And so what I usually look at when I look at a table like this is that I look at the top values and as well as the bottom values. So we can see here that a diagnosis like care involving other physical therapy is really easily predicted by the model correctly. So it's got 100% recall and as well as precision, and an F1 score of 1, which is 100%. So this is a really kind of a reliable category for the model to predict. On the other hand, if you look at some of the lower values, like for example, embolic stroke, the recall score is only 62, which means that we are, only 62% well at predicting the patients that have embolic stroke. So we're missing the extra, 40%. So that could be, a big issue if this is an application that's deployed clinically, because if somebody has the symptoms of embolic stroke, and you're only relying on this AI application, it could miss, a lot of the patients that have this diagnosis. So this is sort of a way that you can use the F1 score, precision and recall to kind of get a sense of, okay, if this model is deployed, how well would it actually inform me in a clinical setting on how many patients will get the right diagnosis versus how many will miss. So that's an interesting way to evaluate. And the support is just telling you how many data points are used to calculate these scores. All right, so we are pretty much at the end. This is just a final example that's kind of fun for you to click on. And every time you click on it, it will choose a random example from the test set. And then it would tell you what the predicted diagnosis is and what the actual diagnosis is. So you can kind of look at the text and see how well the model does and see if you agree with what the model is doing here. And that is the end. Thank you for staying with us for so long, going through the code, but I hope that this has been helpful for you to kind of go over this in detail and to understand what's happening in this notebook.
Folks, this is the brilliant Flora and the model, that natural language processing NLP model that she built for our tutorial. You can run it yourselves. The Colab file is available in the assignment document. We know this is a non-technical course, but we want you to try it. Take a stab at clicking through the Colab file, running the code yourself, and seeing all the different nuance and pieces that make a model like this. So once again, the program is through Michener and Vector Institute. We have the brilliant Dr. Devin Singh, who's instructing this program, and our other fantastic TAs, Jianan and Alex. So this brings us to the end of the coding section. And so we will take a moment and then we will switch over to the PowerPoint. And at this point, you would open up the PowerPoint document, and that should give you a summary of what we've discussed in the actual model here today. And then you should be fully equipped to now go and do your assignment. Thank you, Flora. We'll pause there for now.